Here in 1.6, we're going to be taking a look at solving compound inequalities. We have two objectives. So if you take a look here, our two objectives for this lesson is number one, solve compound inequalities. There's two types there we'll look at. And then number two is solve absolute value inequalities. And again, there's the same two that we'll look at there as well. Just some review. If we take a look at absolute values, if you remember, what should come to your mind when you see absolute values? And that's a key point we got to remember. And hopefully your answer was two cases. Okay, whenever we deal with absolute values, we want to think, especially equations or inequalities, we want to think two cases. Because absolute values deal with distance, and we have distance in two different directions. And so we have two cases that we got to consider. Case one, whenever we solved, if you remember back when we did absolute value equations, we dropped the absolute values and solved. Case number two, we dropped the absolute values, changed the sign of the other side, and solved. That's the opposite case. So we have two cases that we got to take care of. Inequalities, if you take a look, really there's one major thing. We treat it just like an equation, but the only difference is that whenever you multiply or divide by a negative, you have to flip the inequality sign. And so that was that big point. So these are highlights of what we've already done, but we're going to be utilizing these in today's lesson in 1.6. Okay, let's go ahead and take a look at the two types of compound inequalities that we're going to be dealing with today. The first type is going to be an and statement or an intersection. Okay, when we deal with and statements, that means that both conditions or all conditions have to be met for it to be true. And so it must satisfy all the conditions. In discrete math, in some later classes, what you're going to see is a symbol that looks like this. We won't be using that symbol upside down U, but it does represent the and or an intersection. But I wanted to at least show you that. What I want you to think about, and this is the key here, there's a star here for this one, a keynote. I want you to think sandwich when it comes to and statements. Now, one reason the word and is in the word sandwich, so that definitely helps, is the word and is in the word sandwich. But really the main reason is when we're dealing with graphs of and statements. The typical graph, okay, not all, but the typical graph of an and statement, they go towards each other. Okay, so what you have is like a piece of bread here, a piece of bread here, and guess what's in the middle? It's the good stuff. It's the meat. Okay? That's the solutions. So what we have is we have an endpoint, and we have an endpoint. Sorry for being a little sloppy there. Okay? But then we got our solutions found right in the middle. Okay? And that's our and statement, intersection. If we take a look at it here, a little bit more in depth, there we go. We got a piece of bread, everything in the middle are your solutions because there's an overlap, and we'll see that graphically in just a moment. Okay? Now, when you put your answers in an and form, we want to put it in a sandwich form. So this right here is very important. This is how you would put your solutions for and statements when you get the typical type. So what you have is your lower bound, or your lower number, the smaller of the two, and then whether it's less than or equal to or just less than, and then your upper value. Upper bound is what we have there. Taking a look at these examples here, the first one is x is greater than or equal to -1. This inequality we can do just individually. We say, oh, we go to -1. We've already done this. It's going to be closed at -1. And notice that my solutions are greater or to the right. So you can see that right there. And so if in red, I go ahead and do step number 2, which is x is less than 2. It's going to be open at 2. And notice it's going to be going that way. And so there's our graph. Now what we're looking for with an and statement is an intersection or overlap. And so I could try to drag this down like this, and you can sort of see the overlap where, in this case, red and blue would make purple. And so where do they overlap? Well, they definitely are going to overlap right here at -1 because it includes that value. And then they overlap everything in between. There's your sandwich. Until you get to 2, and then 2 it's open, so we got to leave it open for an and statement. And there's your solution to this and compound inequality. Now to write our answer, you can just simply look at the graph. It makes it a little bit easier and say, look, my solutions, the meat of it is sandwiched in between 2, not including 2, and -1, but including -1. And so here's our algebraic notation of putting it, and there's our graphical approach, okay, of doing this problem. Moving on, taking a look at and compound inequalities again, a different look. Instead of having the word and, they may be already written in the sandwich form like this. So what our goal is to isolate the variable that you find in the middle. And so like here, the x. So I'm going to put a box around that. That's what I want to do is isolate. Not on one side. You can see there's 3 sides now. You got a left, a middle, and a right. So we want to isolate it in the middle. And so what we need to remember is this: whatever you do in the middle, you got to do the other two sides. The other two sides, keep that in mind, it's not just one. And so we go ahead and we say in this case, all right, so to get x by itself, I've got to subtract the 7. It's almost like covering up this part right here and just looking at this inequality. And a lot of texts show you that, and I think your text will show you that. But I like doing it all at once, and so we're going to learn that. And so we would go ahead and subtract 7. Whenever you do the middle, you got to do 2 ends. And so we still have that 2x. This is gone. And so we're getting that much closer to getting x by itself. Again, this is what our objective is to get the x by itself. So I need to undo this multiplication of 2, so I'm going to divide by 2. Whatever I do the middle, I do the 2 ends. So I'd have 3, and then I've got x and 5. And notice the x is by itself. Bam, there we go. Nothing really tricky about that. When we go over to graph it and we say, well, our lower bound is at 3. It's not going to include 3, so it's going to be open. Our upper bound's at 5. We go ahead and close it off, and there we go. Okay. If we take a look at the bottom one, we want to be very careful of this third sort of rule, is when you multiply or divide by a negative, you must flip the inequality sign. Where have we heard that one from? From the inequalities. And so anytime you deal with inequalities and deal with negatives, you got to be careful. But again, our goal is to get this x by itself. And so we go, well, how do we go about doing this? And so we go, well, I've got to move the constants first. So I've got to undo this negative 4 or subtraction of 4 by adding 4. So that would be the first phase of what we're doing. The second step's the one. This is the one right here. Notice to get x by itself, I divide by negative 3. So right here on this step, I have inequalities. I'm dividing by a negative. Anything you do in the middle, you got to do the 2 ends. So we have this right here. That's definitely going to give me x in the middle. Okay, so that's great. But because I'm dividing by a negative, I have to flip these inequality signs, and that's tricky. But I need to flip both inequality signs, and I end up getting negative 4 and negative 5. Now, this isn't technically how we like to write it. We like to put our lower bound. Negative 5 is smaller than negative 4. So we usually would just flip everything over. The alligator's eating the x, and the alligator's eating the negative 4. So either one I would have accepted. This is a little bit more appropriate for what we're doing. But now if we're going to go ahead and graph this, we'd say, well, it's going to be open at negative 5. It's going to be closed at negative 4. And my sandwich is right there. Okay? And there's your graphical solution to this problem right there. Those are and compound inequalities. Move on and take a look at or compound inequalities. What we've got going on here is a union. Only needs to satisfy one of the conditions to be a solution, not both. You definitely will be seeing this union symbol, which is just a U, which represents an or statement. Now, I want you to think or, and you can see the word or, when you say the word or, you say the word or. But I'm not saying O-R, or, I'm saying O-A-R, like you're rowing a boat with oars. Now, the reason I say that is typically or statements go away from each other. So what you have here is you've got a start point, and you've got a start point, and you're going this way with your solutions, and it's not a sandwich, but it's like you're rowing a boat. They go away from each other. And so you can see that. Let me go ahead and just get rid of this. Hey, right there. Hey, you got your, where's the important thing at? Well, it's in the boat, but in this case, the things that allow you to move or your solutions are the oars. Hey, right here. So you got the start point, and the or goes out this way. And then you got start, and then your solutions go out that way. So typically, ors will do something like that. Now, when we put our solution in for ors, what we want to do is we simply want to put it in this type of form. So make sure to note that with the word or in it. So we don't want to write ors as ands, as sandwiches. We want to write the word or in the solution. Okay? So let's take a look at an example and see how this works. Again, what we have going on here is x is less than or equal to 1. We go to 1. It's going to be solid. Let me go a little faster on it now. And there we go. And then x is greater than 4. It's going to be open. It goes this way. So if I go ahead and again take this, really take them both, and I come down here and I put them together, notice what you have is you have ors going away from each other. And so typically for an or statement, it only has to satisfy one of the two conditions, which it does if it's a 1 or anything less than 1, and it does if it's anything greater than 4. It can't be 4. It's anything greater. So the blue is our solution. How do we write that solution? It's right here. You take this, you slap the word or in the middle, and there you go. That's pretty much it. Ors are pretty easy to write. And taking a look at a couple more examples of ors. I'm going to work through these fairly quickly, so you can rewind if you need to. On this one, I need to get y by itself, so I'm going to add 2. So isolating the variable we get this. Has the word or. This one I subtract 1 to get the y by itself. I don't need to flip anything because I did multiply or divide by a negative. Now I'm going to graph each one separately. So y is greater than 3. Going to be open, greater meaning to the right. Y is less than or equal to -4. There's my closed. And it's less than, oh, there's your typical. Now what I have is, once I see the graph, I'm going to go ahead and square it. I wouldn't put a box around it until you see the graph, because we will have some weird ones that you'll want to make sure to see before you put your final answer. And we'll look at one of those here in a little bit. But subtract 5 on this one, and you get less than or equal to 2. Got the word or, just keeps coming. Add 6. You know, I haven't multiplied or divide by negative, so no need to flip anything. So I have y is less than or equal to 2. And so it's going to be closed, and it's going to be less than or equal to 2. Or y is greater than 4, and so that's going to be open at 4, and it's greater than 4. And so that's a pretty typical or. So I come over here, I circle my answer, and there we go. That's as far as you go graphically and algebraically. Okay. Now moving on, let's take a look at really our second objective, which is the absolute value inequalities. Now with absolute value inequalities, it's not as easy to identify the ands and ors. And so we'll talk about how to address those, but the first things first, and we mentioned this earlier in this lesson, is when you see an absolute value, what should come to your mind? 2 cases. When you see an absolute value equation, 2 cases. When you see an absolute value inequality, 2 cases. So anytime you deal with 2 of something, that's called a compound. Compound inequality is what we have going on because we have 2 inequalities. So let's talk a little bit about the procedure of how do we go about solving for a compound absolute value inequality. And so you look, and step number 1 is isolate the absolute value. No different than when we did absolute value equations. You want to go ahead and isolate the absolute value first. Move all the constants and coefficients. Anything outside the absolute values need to be moved to the other side. At that point, then you need to establish whether it's an and or an or. This can be done very easily. We'll address that right down here. It takes a little bit of memorization, but man, once you get it, you got it. Then what you want to do is create your 2 cases. Case 1, drop the absolute values and solve. Pretty easy one. Case 2, there's a lot here on case 2. This is where we make our mistakes. Case 2, drop the absolute value, change the sign of the other side. Remember, that's what we did with equations too. But in doing so, what we've actually done is multiplied the side by a negative, which means we need to flip the inequality sign, then solve. A lot going on in case 2. That's the one you want to note. Make sure you get that one down in your notes. Step 4 is write your solution in the correct format. So if it's an and, we want to write it in the sandwich form. And if it's an or, then we'd write our answers with the word or in there in some manner. Let's go back to number 2. Establish if it's an and or an or. Once you isolate your absolute value, you'll have absolute value of something. And you're either going to have greater than or equal to, less than or equal to. The greater than or equal to. Take a look at these two because they're grouped together. If I slow down and say these just slightly different, instead of saying greater, if I say the word greater, okay, that's going to indicate to you the absolute value is greater, or the absolute value is greater or equal to. That's going to tell you that we're dealing with or statements. So you don't see the word or anywhere. You got to know which one it is. And some ors look like ands, and some ands look like ors when you graph them. So how can we determine it without graphing? Here's how you do it. Absolute value, greater, absolute value, greater, or. Down here with these, if you take a look, you have absolute value is less than, absolute value less than. Instead of less than, what if I said less than? Okay, so very close, but that's going to help you determine what we have here is we have an and statement. So if you have the absolute value is less than, that's an and. So you know typically it's a sandwich, but not all the case. What you will know, being that it's an and, is that we're looking for an intersection. It must satisfy both conditions. We're over here, we're talking about a union. Okay. So that's the key, is making sure we distinguish between the two. And that's a great way of doing that. Okay, let's move on, take a look at some examples of these. And if you look at this first example, we have the absolute value, which is isolated already. That's great. That's the first thing we want to do. Then we want to establish if it's an and or an or. Well, notice what it is. Absolute value is greater or equal to 6. It's an or statement. So typically, ors go away from each other. Okay, not always, but typically. Okay, so let's see what we get. Case 1, this is how I want you to set up your work here. Case 1, drop the absolute value. So simply get rid of the absolute value and solve the inequality. So I'm going to go ahead and add 12 So we'll go through this and add 12 to both sides. I got to get the x by itself. That's what I'm trying to do, is get x by itself. So we have 3x is greater than or equal to 18, and then we want to divide by 3 to get x by itself. Again, we undo that, and then we get this statement, x is greater than or equal to 6. Now, remember, it's an or statement, so I'm going to go over here. I don't even have a 6 up here, so I better put a 6. And then I've got close it in, and it's greater than or equal to 6. Then we move on to do the second one. And so case 2. Case 2 is the tricky one. This is the one we got to be careful of. We still drop the absolute value. That doesn't change. What changes now is the 6 becomes a negative 6. Now, what allowed me to do that? Well, I multiplied by a negative 1. I changed its sign. If you change the sign, you flip the inequality sign. You change, you flip. You change, you flip. You change, you flip. So we changed, we flipped. Now we go ahead and we can isolate our variable again. So we add 12. And we get here, and then divide by 3. Boop, doop. And what we get here is 6 divided by 3 is 2. And so we get this answer of x is less than or equal to 2. So we go to 2, it's going to be solid, and then we go less. There's your typical or. See how the graph is very typical? Good. Okay, now we still need to write our answer. And so our answer is going to be taking this and this, but slapping the word or in between. So I always put the smaller one first. Again, I wouldn't count it wrong if you put flip-flopped them, but that would be your final answer algebraically and then graphically. Taking a look at this one right here, we have an absolute value is less than 21. Well, we get the absolute value by itself, which it is, and then less than and less than. That's an and statement. So typically ands are sandwiches. Okay, in this case they'll probably be open instead of closed. But we do want to set up our two cases. So case 1, drop the absolute value and solve, so we don't change anything. So we don't flip anything. So we're going to add 3 to both sides. And then divide by 6 to both sides, and what you get is you get r is less than 4. So it's going to be open at 4, and it's going to be going that way. So I'll get you that graph in there. Case 2, that's the tricky one. Case 2, we drop the absolute values, we change it, we flip it. Change, flip. Change the sign, flip the sign. Change the sign, flip the sign. Now we can go ahead and get r by itself is what our goal is. And so if I want to get r by itself, then I'm going to need to add 3. First move the constants first. So all those wonderful things we've been working on. Divide by 6 next. And divided by a positive, so I don't need to flip anything again. That could happen. I may have to flip it again, but not in this case. So I have r is greater than negative 3. So I go to negative 3, and it's going to be open, and I'm going to go this way. Now, remember what we're doing is this is an and statement. So what we're looking for is the intersection of the two. Where do they overlap? They start overlapping right here. See how they overlap? Boom. And then they stop overlapping. So my solutions, really technically, I don't want all this stuff outside anymore. Okay? Because that's not part of my solutions. My solutions are in between negative 3 and 4. So if I wanted to write my final answer to this, remember how we want to write our solutions to and statements are like this, and because it's not or equal to, I don't put or equal to. My low value is negative 3, my lower bound, and my upper bound is 4. And bam, there you go. There's your sandwich for your and statement. Okay. Moving on, we got ands that look like ors and ors that look like ands. This is the last thing we'll take a look at. And these are the tricky ones. You don't come across a lot of these, but they are a little tricky. Notice here we have the absolute value. We got to isolate it by itself. It already is. Less than. So this is an and. Okay, it's going to look like an or, obviously. Now you can use your common sense, and you can see absolute values, which the result of an absolute value is always positive. So how can a positive ever be less than negative 5? Interesting. Okay, so something you could have identified right from the get-go. But let's work through this. Okay, I'm going to work fairly quickly here. 3x plus 1 less than or equals to negative 5. And then we want to get x by itself. And so we go through this process here. And we get to this point right there where x is less than or equal to negative 2. So we go over here. Seems good so far. Case 2. Drop the absolute values. Change the sign. Change the sign, flip the sign. Change the sign, flip the sign. Now we go ahead and we isolate the variable again. And ooh, we get a fraction. Yay. So there we go, 4/3. Now when you come down here to graph 4/3, that's 1 1/4, or 1 1/3, excuse me, 1 1/3. So just get close. You're right here. That's good enough. Okay, but it's going to be greater than or equal to that. No, okay, now look at this. Notice the graph looks like an or. but we said it's an and. So if I said, well, where do they overlap? Where's the intersection? Well, hopefully you notice they don't overlap anywhere. If they don't overlap anywhere, then if I said the solutions are where they overlap, put 2 and 2 together here, no solution. Okay, so if you get an and statement that looks like an or, you've got a no solution. So technically on our graph, we shouldn't have anything because there's no solution. The graph allows us to see that there is no solution, but we'd want to put our final solution to the graph blank. That's an and that looks like an or. An or that looks like an and would be one like this one. Now this is a good one because we have not got the absolute value isolated yet. You must go ahead and subtract the 4 before you start this problem. Now if you look at this, remember the result of an absolute value is always positive. So is a positive always greater than or equal to -3? True. This was called a false statement. This one's called a true statement. So the one up here, the and that looks like an or, is always false. This one's true. So you can identify it right now. You have a good chance of getting the answer before even doing the problem. But let's go ahead and do the 2 cases just to get through it. So I subtract 1. There's my first one. X is greater than or equal to -4. So here it is. And I go this way. And then my second one, I'll do in blue. Case 2, be careful on case 2. Drop the absolute values. Change the sign, flip the sign. Change the sign, flip the sign. Subtract your 1, and you get x is less than or equal to 2. Okay, now notice here, it looks like we want to do the intersection, but it's not an and, it's an or. Okay, and so it only has to satisfy one of the 2. And if we take a look here, it satisfies at least the blue or the red at all points. Give me a number, and I guarantee you the blue or red is going to cover it. So what we have here is an or that looks like an and. It has crossed. And anytime you get an or that looks like an and, you're talking about all reals is your solution. Any number is your solution. Now, how do we do that graphically? Okay, what you want to do is simply, this is pretty easy. You just simply take and you cover the whole number line. The whole number line is your solution, so anything that works. And your answer, again, would be all reals. You wouldn't want to put the word or in this case because we have an answer called all reals. That is section 1.6, compound inequalities and absolute value inequalities. See you next time.